So there are many different type of integrals. So when it comes to evaluate those integrals, it can be very time consuming. So in practice, what we're gonna do is, so there are like what we call table of integrals. So what we're gonna do is we're gonna match the integral with one of those integrals and use them and try to find it. Because these integrals appear in many different applications in physics, engineering, and a lot of other fields. So so we are not gonna integrate every time when we get something like that. So what we're gonna do is we're gonna match with those what we call table of integrals. So the purpose of this discussion is how to use them, and we start with what we call reduction order formulas. So that means if we have a power formula, like for example sine 10 dx. So if you have something like that, so you can use the repeated trigonometric integrals, or what we can do is we can relate a higher order integral to a lower order integral. So for example, if we can relate the integral of 9 sine 9 to integral of sine 8, so then we reduce power by 1, so then we can evaluate 8. Now to evaluate 8 we can evaluate 7, so like that. So so those kind of relations are what we normally call reduction of order formula, because we reduce the power of the formula. So let's discuss about that. So reduction formulas. uh, so so what's the reduction formula? We can write an integral with a lower power. So we can write an integral, right, an integral with a lower power. So we're gonna write using a reduced power. So then every time when you use the formula, it's gonna reduce the power. So so there are several very important formulas. So let's talk about some of them. Um, so several important formulas. So several important formula. So for example, let's say I'm gonna write A. So sine n x dx. So you can relate this sine nx dx to negative 1 over n cosine x sine n minus x dx, n minus x dx, n minus x uh, plus n minus 1 over n, the integral sine n minus 2 x dx. So this formula works for any integer greater than or equal to. So you can see that so sine n, now you relate to sine n minus 2. So that means if you want to find sine 8, you actually need to evaluate sine 6. And to sine 6, you can evaluate sine 4. For sine 4, you're going to go evaluate sine 2. So like that. And then for sine 2, it's simply sine 0, which is one constant. So that's how we use the formula. So I'm going to give you a few more formulas like this. We have these two, one for one for cosine. So cosine nx dx equal 1 over n cosine n minus 1 x sine x plus n minus 1 over n cosine n minus 2 x dx. This also works for an integer which is greater than or equal to. And then for tangent, tan nx dx equal 1 over n minus 1 tan n minus 1 x minus tan n minus 2 x dx. And then we have three more for secant and exponential and log functions. So we have these three also. So secant nx dx equal tan x secant n minus 2x over n minus 1 plus n minus 2 n minus 1, the integral of secant n minus 2x dx. And then we have for the power function xn ex dx, which is equals to, so we have xn ex dx equal xn ex minus n times xn minus 1 ex ds, and you can see that the xn become xn minus 1, so one power goes down. And then we have as the last one, we can write the natural log x to the nth power dx, which is equals to uh, this is equal to x ln x to the n power minus n ln x in minus 1 dx, and you can see that ln to the n power now became minus 1. So the question is like, whether do you want to remember this? So we don't want to remember these for exams. So what's going to happen if you want to use something like that? We're going to give you the formula, and then you are given the formula. What you want to do is you don't need to know how to use them. Okay. So, but you don't want to remember these formulas because nobody can remember these formulas. This is normally you can find them in at the end of a textbook. So what we're gonna do, we're gonna prove only two formulas just to show you how to do that. So we normally use the most of the problems we use the integration by parts. So we use integration by parts to prove them. Okay, so we're just gonna prove two formulas. We're gonna prove the first one and the last one just to see how it works. So let's prove the sine formula first. So we're gonna prove the first one, so which is the sine nx dx. So what we normally do is we're gonna pull out one sine term. So we're gonna say sine n minus 1 x and then sine nx dx. So we're going to pull one term out, and then what we're going to do is we're going to use integration by parts for this. So let's try the integration by parts. So what we're going to do, I'm going to pick this part as u and this one as a dv. So u equal sine n minus 1 x and the dv equal sine x dx. Uh, so dv equal sine x dx, and then you can see it's a du, so take the derivative, so which is n minus 1 sine n minus 2x, and then take the derivative of the sine, which is cosine x dx, and from the other one we say v equal, this is sine, so that means negative cosine x. So that's what you get. Now we're going to plug in those four into the formula. So we're going to get which is uv minus v du. So let's plug it into them. So uv, we have u and v, so that means you get negative cosine x, that's the v, and then we write the u, so which is sine n minus 1x, and then there's a negative sign and v has a negative sign, so it becomes plus, and then so v, which is cosine x, we put the negative sign outside, and then du means n minus 1 sine n minus 2x cosine x dx. Now what we can do, we can do some simplification. We can I'm going to rewrite this one. So cosine x sine n minus x plus, I can pull the n minus 1 out and then combine the two cosines. Once you combine the two cosine, so you can write this one as cosine squared x and then sine n minus 2x dx. Now cosine squared, from the Pythagorean identity, we can write this one as 1 minus sine squared. So we can write it like that. So negative cosine x sine n minus 1x plus n minus 1. So we can replace this one by 1 minus sine squared x and then sine n minus 2x dx. Now we can distribute them into two integrals. So we can write this on negative cosine x and then sine n minus 1 x plus, you can write this one as two integrals. If you from the first one, you're going to get n minus 1 times sine n minus 2x dx. That's the first one. From the second one, which has a negative sign, if you combine this, you have a square here, n minus 2, so they're going to cancel out, so you get sine n term there. So that means the next one is negative n minus 1. So once you combine, this becomes sine n x dx. Now what I'm going to do, I'm going to move this term to the other side. Once you move this term to the other side, you're going to add up. So you're going to get n, and then you're going to divide the whole equation by n. So you finally get sine nx dx. So you divide by n. That's why you get negative 1 over n, because you divide. And then cos n sine n minus 1, not 2, n minus 1x, plus here n minus 1. Now you divide by n. That's the term you're dividing. And you have sine n minus 2x dx. So again, what we did, because you can see there the sine nx dx term, I'm going to move that term to the other side. So then there's a 1 on the other side, so they're going to add up. So you get n many of sine n, so you can divide by n. So that's that n we divide both sides. So you're going to get this formula at the end. So you can see the major technique was integration by parts. And at the end we did some kind of algebra, and we also used the Pythagorean identity here to replace the cosine squared term. Okay, so that's how you do it. So most of those formulas, all of those formulas, we use integration by parts to prove. So we're gonna prove just one more to show how things gonna work. So let's prove the last one. So we have f, so which is ln to the nth power dx. So again, we can use integral parts for this problem as well. So we're gonna pick u equal, this is because this is a natural log, so that means we pick natural log as the function as u, and then dv equal dx, so it's obvious. Now we take the derivative, so du equal n ln n to the n minus 1, and multiply by the derivative of the inside function, which is 1 over x dx. And then here we get v equal x. So we have all four. Now we're going to plug in there. So that means uv. So this is v, and the u is ln n to the nth power minus vdu. So you can see there's an n, so I'm going to write it outside. So we have v, that means x, and then du. So we already write n outside and write the rest. So ln n to the n minus 1, 1 over x dx. And then you can see that x and x get cancelled. So you finally get, so this is an easy one, ln n to the nth power minus n times ln n to the n minus 1 dx. Okay, so that's the formula. So that's a like easy one. Now let's try to see how we can use them to evaluate certain problems. So I'm going to do a couple of examples, and theory is over, so we do like a couple of examples to see, learn how to use them. So so as the first example, let's try this one. So you can evaluate the integral of 0 to pi over 2 sine, let's say, fifth power 5x dx. So what we can use the first formula with n equal 5. So if you use n equal 5 in the first formula, you can see that it is negative 1 over 5 cosine x, and sine you subtract 1, so it becomes 4x. Now this is a definite integral, so you can evaluate at pi over 2 and 0, and then plus n minus 1, that means 4 over n. The integral goes 0 to pi over 2. Sine you subtract 2, that means it's going to be 3x dx. Now what we're going to do, we're going to evaluate the first one, and you can see that when you evaluate the product at the 2, you can see one of the function is 0. That means this whole thing going to be 0, because one of the functions gets 0 either at 0 or at pi over 2. So that means the product is 0, so that means gone. So we only have 4/5 the sine cube power. That's again we can use the formula again. So if you use the formula again, you're going to get now with n equal 3. So that means negative 1 over 3 now. Again cosine x sine, now we have 2x. Evaluate at pi over 2 0, plus 2/3, subtract 2, so it's going to be sine nx dx. That's what you get. Now again, same argument. This gonna be 0, so it's gone. And then you're gonna get 4/5, 2/3. So you can evaluate 0 pi over 2 sine x dx, which is easy. So this is like 8, 15. So this is going to be a negative cosine x pi over 2, 0. And once you plug in the values, and you can see at pi over 2 it is 0, at 0 is 1, with the negative sign is positive. So 8, 15 is the final answer. What we did, we used a reduction formula 2 times, one with n equal 5, the other with n equal 3. Okay, so use the reduction formula 2 times to evaluate this formula. Okay, so let's do one more problem. How about this one? Uh, let's say we have tan squared x secant cube x dx. So this is one of the trigonometric integral. So and normally when we have tan odd power, we know how to do it, but now we have a tan even power. So when you have tan even power, our regular technique does not work. So what we're gonna do is and also secant has the odd power. If secant has an even power, we have a way to do it, because we can pull out secant squared as the derivative and go with the tan function. So the secant has the uh, even power, tan has the odd power, so regular technique does not work, because if tan has the odd power, we're gonna go for tan substitution. If a secant has an even power, we're gonna go for a secant substitution. But this have completely opposite, so that means this doesn't work. But what we can do is we can rewrite tangent as secant squared x minus 1. This is one of the trigonometric identity, and then secant cube x dx. So we substitute for tan squared by the Pythagorean identity. Now we're going to split the two. We're going to multiply through. So that means if you multiply the first one, you're going to get secant 5x dx minus, if you multiply the second one, you're going to get secant cube x dx. So that's what you get. Now what we're going to do is we're going to use the formula, the secant formula twice. So let's first use the secant formula, the first term. So if you use for the first term the secant formula with n equal 5, the secant formula, so which is you're going to get tan x secant cube x divided by n minus 1, that means 4, plus 3/4, you're going to get secant cube x dx. That's from the reduction formula. We use n equal 3 for the reduction formula, and we don't do anything with the second one. I'm going to leave it like that. You're going to see the reason. Now what you can do is you can combine these two. So I'm going to combine these two into 1. So it's just a subtraction. You have 3/4 and minus 1, that means you get negative 1/4. So I'm going to write it like that. So you can write this one as tan x secant cube x over 4, and if you subtract, you get negative 1/4 secant cube x if you simplify the last two integrals. Now we can use the reduction formula for that. So if you the reduction formula here, so you're going to get tan x secant cube x over 4, and then now we're going to use the reduction formula for that term. So if you use the reduction formula here, you're going to get tan x secant x over 2 now, because n equal 3. You can use n equal 3 for the formula. Actually earlier we made a mistake. It's n equal 5. So it's n equal 5. Okay, so so you're gonna get plus 1/2 secant x, 1/2 secant x dx. Now secant x, we know how to integrate secant x. So then I'm gonna write the final answer here because it's a little long. So you get 1/4 tan x secant cube x minus 1/8 tan x secant x, and then negative 1/8 again. We know secant x, that's one of the formula that is natural log secant x plus tan x plus c. Yeah, so that's about that. So you can see that we use one of the trigonometric identity and we use the reduction formula twice. Reduction formula for secant twice to get the final answer. But for that one, we also use a trick. We did not do a substitute for for both first. We only substitute for the first one, and then after you get the secant one, we simplify the secant and then substitute again, because that's going to reduce the work that you need to do. So you have to think first before you kind of try to do something just to reduce the calculation. Okay, now what we're gonna do, we're gonna do several other problems using the tables. So let's see how we can use the other integrals from the table. So you can look at whatever the book that you use, look at the end of the book and you can find the table of integrals. So you're gonna see several integrals with different patterns. So there are about 200 300 tables, but there are like thousands of them. But in a textbook you can probably find like about 200. So there are a lot of different things. So if you get a different integral, what you can do is you can match with them and then write the solution right off. But sometimes you may have to use some kind of substitution just to make sure that it's gonna bring it to one of those forms. So let's look at this problem as the next one. So I'm going to say table of integrals. So table of integrals, table of integrals. So let's say let's start with this problem. Let's say we have x squared divided by 5 minus 4x squared square root dx. First you can see that you can rewrite this problem like this. So x squared over 5 minus 2x squared. So you can write this as 2x squared just to bring it to one of the forms. Now what you can do is we can use like kind of obvious substitution. So let's see what kind of formulas that you can find. So for example, if you look at the textbook, you can find a formula like this in textbooks. So there's a formula for u squared over a squared minus u squared square root du. So this one you can actually prove using substitution technique, trig substitution, but you can use this as a formula, uh, not in exams. Okay, so in practice. So this is the formula. So plus a squared over 2 sine inverse u over a plus c. So this is the formula. So what you want to do is you need to bring it to this format. So this is one of the formula you can find in a book. You may see this form or something closer to this. So what you want to do, you want to bring it to this form. So you can see this is not exactly like that. So to bring it to this form, what you can do is you can substitute u equal 2x. So if you substitute u equal 2x, then this says that x equal u over 2 and also du equal 2 dx. So what you can do is you can substitute that in the integral. So I'm going to write it here. So what's going to happen, so your integral now becomes under this new variable, you can say x becomes u over 2 squared, and here this become 5 minus 2x, that means u, so u squared square root du, and then also dx, actually dx is du over 2, so it's du over 2. Okay, so let's simplify this a little bit, and you can see from the top you're gonna get 1/4, and also you get 2, so 1/8 you can pull out, and then you're gonna get u squared over 5 minus u squared square root du. Now you can see this very well match with the formula that we have, and then you can see that a equal square root 5. So just plug in a equal square root 5 in the formula, and then you can get this one. So if you plug in that, you're going to get 1/8 negative u over 2 5 minus u squared square root plus a squared means 5 over 2 sine inverse u means this is u, so it's a u over a means square root 5 plus c. Now what you need to do is you want to put the u back in the final answer. So we get the answer now using the formula, and then so we use this formula right here to this. Okay, you can substitute for that. Now what you're going to put u back in. So let's substitute for u. If you substitute for u, you can see negative 1 over 8. U equal 2x with the 2, so it becomes x, and this is 5 minus u means 4x squared square root minus 5 over 16 sine inverse u means 2x, so it's a 2x over square root 5 plus c. So that's the final answer using one of those formulas that you can find in a textbook. So let's do let's do 2 more examples. Let's do another one. So this is about sine polynomials and sine. So let's do this. So we have x cube sine x dx. Now so what we can do, we can use one of the formulas again given in the book. So I'm going to write the formula first. So this is the formula we can use. So there's a formula that's called un sine u du equal negative u to the n cosine u plus n u n minus 1 cosine u du. So this one easily you can integrate using integration by parts. And also there's another formula because you can see that once you reduce the power, this cosine sine become cosine. So you see sine convert to cosine. That means you also need the cosine formula. So let's try the cosine formula also. So the cosine formula is un cosine u du equal un sine u minus now plus on the plus and then u n minus 1 the other type, so sine u du. So those are the two formulas. So let's use these two formulas now, okay, and then see what we can do. So again, in the exams you will be given those formulas, so you don't recall it, remember anything. Who can remember this? So sin x dx. So I'm going to use the first formula. So if you use the first formula, you get negative x to the n means 3. So you put n equal 3 in the first formula. So you get cosine x plus 3 x squared cosine x dx. Now you can see you have to use the second formula. So if you use the second formula now, you're going to get, so we have negative x3 cosine x from the first one, so you can leave it, plus, so let's use that. So it's a 3 times, so I'm going to put inside bracket. Now let's use the second formula. So with the second formula, it's going to be x squared, the other type, so sine x minus 2, the integral x sine x dx. I'm not going to add the c yet, okay? And then you can see this one just the integration by parts problem, or you can use a formula for this one, because this is like we try to use formulas. So if I'm going to simplify this a little bit first. So it's a negative x cube cosine x plus 3x squared sine x minus 6 integral x sine x dx. And also you can use another formula or you can use integration by parts. So here's the formula. This is what you get. I'm going to write the result and write the formula next. It's kind of weird. Okay, so cosine x plus 3x squared sine x minus 6, and then there's a formula from the table. You can see that this is simply sine x minus x cosine x. Now I'm going to see, because that's the last one. So this, where this is coming from, the last one is this formula. So what the formula we have u, the integral of u sine u du, which is equals to sine u minus u cosine u plus c. So that's the formula we use for the last part. So that's what we get. Okay, so that's about that. And then what you can do is you can simplify this a little bit. So I'm going to let you do that. You can combine, I mean, just distribute write it without parentheses. Okay, that's how you use some of the formulas. So for this problem, we use 3 formulas. So let's do just one last problem. So this is the last one we do. Number C. So let's say we have a problem like this, like a little complicated. So x squared plus 2x plus 4 square root dx. So what's going to happen is, so there is a formula which says that, so I'm going to give you the formula first. So let's try the formula. So what we're going to do first is, before we use the formula, we normally have like a complete square. So we're going to do the complete square first. So we can write this one as x. You can see inside, you can write this one as x plus 1 whole thing is squared. If you square this one, what do you get? You get x squared plus 2x plus 1. So that means you have 3 left. So you can write it like that and take the square root. So you can write it like that, dx. Now what we can do is, we can use obvious substitution. So you can see, you can substitute for the inside function this part. So you can call this is u. That's the kind of obvious substitution that we can try. So let's say u equal x plus 1. So in that case, so this says that x equal u minus 1, and also du simply equals to dx. That might be useful later. So if you do that, then what's going to happen is, you can write x, which is u minus 1. Inside, you can see this is u squared plus 3 square root. Dx is simply du. So you can write it like that. Now what we can do, we can split this into true integrals. So you can write the first one as u, and then u squared plus 3 square root du, and then minus the other one is u squared plus 3 square root du. The first one is easy. You can just use the 4 formula trick, because you can see the derivative of the inside function is just 2u. So what we can do is, we can write 1/2 2u, and then u squared plus 3 1/2 du. I'm going to rewrite this one because we can use a formula for that. X squared plus 3 square root du. And then this is simply from the 4 formula trick, because that's just the derivative. So that means this is 1/2. Just treat this function is x. Simply treat this one as x. So that means it's going to be 2/3 u squared plus 3/3. So that's part is done. The minus, we have this one u squared plus 3 square root du. For that we can use a formula. So if you actually, you can also just a simplification going on here. So you're gonna write this one as 1/3 u squared plus 3. We have 3/2, and then minus this one. This step is not really necessary. I'm just repeating it just for clearance. Okay, now what we can do is, we can use one of the formula. So the formula says this. So the formula says the integral of a squared u squared square root du, which is equals to u over 2 a squared plus u squared square root plus a squared over 2 natural log u plus a squared u squared square root plus c. So that's the formula. So if you use this formula and also plug in back from u, see whether you can get this as the final answer. So final answer for the integral x squared plus 2x plus 4 square root dx should be equals to this. So you should see that 1/3 x squared plus 2x plus 4 to the 3 halves minus x plus 1 over 2 x squared plus 2x plus 4 minus um, 3 halves ln x plus 1 plus x squared plus 2x plus 4 a bracket plus c. So that's the final answer for this problem. So for these problems you are given the formula and then you should be able to use the formula. So normally what you need to do is to find the proper substitution so that it's gonna bring it to the formula that you're gonna use. So only thing what we did is we use a formula to evaluate um, this part of the integral. So we use a formula to evaluate this. Okay, good. So that's the end of the video.